I want to thank everyone for joining us here for this edition of MooreChat. As you know, these are brief 10-minute talks in which we have one of our resident experts speak on a topic if they're choosing something that's near and dear to them and they're quite familiar with. Speaking today will be Mr. Chris DeRosa, who is uniquely in industry, a licensed professional engineer and a licensed architect. Couldn't decide which one, so just went ahead and did both ambitiously. Chris is located in the Washington, D.C. office and is providing services from our diagnostics group in that general locale. Chris specializes, in addition to being just an overall great guy, one of our favorite people in industry. Chris specializes in architectural investigation and design of a wide variety of building enclosure systems and materials, from historic masonry to contemporary glazing systems, to name a couple. Since joining us here at Walter P. Moore, he's been involved in a number of different types of projects, focusing on historic preservation, repair and rehabilitation design of facades and enclosures, facade condition assessments and investigation, as well as roofing and waterproofing consulting for both new, existing, and historically significant structures. So with that, I will go ahead and turn it over to Chris to dive into our today's version of the MooreChat.
Thank you, Derek. Appreciate it. What I'm going to be covering is just one portion of a larger restoration project of Toronto's Rogers Centre that Walter P. Moore has been involved in. It is the restoration of the roof, and going to be speaking about the different phases from assessment, design, and all the way through construction. And if I do it right, I'm hoping to get this presentation, get through it all in about 10 minutes, which is half the time it takes for the Rogers Centre roof to open up. So let me get started. Most folks are familiar that the Rogers Centre is home to the Toronto Blue Jays. But there's a lot of other different events that occur at the Rogers Centre, musical, sporting events, and other cultural events that happen year round. And one of the reasons that is so successful, in my mind, is a defining feature of the stadium, and it's the operability of the stadium roof. When the Rogers Centre opened in 1989, it was one of the first stadiums in the country to have a mechanized retractable roof. And here's an aerial view of the Rogers Centre, and I don't think this gives justice just to the scale of this stadium, where it's almost 300 feet tall, 700 feet diameter, and 460,000 square feet. That's surface area of the roof. And where it's situated, you can't see it in this aerial, but it's right adjacent to Lake Ontario. And then at the top of that image, you can see the base of the CNN Tower. So it's right adjacent to the Rogers Centre Stadium. And when you think about the roof, it's not a single monolithic construction, but the roof system is made up of 4 major panels. And panel number 1, panel number 4 are these quarter domes, and then panels number 2 and 3, those are barreled arches. And so I really like this diagram. So this is a section cut through the 4 different panels, and not showing any of the other stadium for. And on the top is a diagram of those panels in the closed position. And so what happens is, for panel number 1, there's a circular rail or track that the panel is able to rotate around. And then you can see in the bottom where that panel number 1 is positioned. Then for panels number 2 and 3, those are on linear tracks, and those shift over, and so that all 4 panels are positioned over number 4, which is fixed. And so that's what's showing right here, the stadium in an open position. And this is a great image. This is just showing those rails, those linear rails for panels 2 and panels 3, just to give you a sense of the kind of scale that we're talking about, and that these roof systems are bearing on these tracks, and they're independently able to move and go into that closed or open position depending on the needs of the stadium. And here is an overview of the roof assembly that we have existing conditions at the Rogers Center. And so starting at the top is a original single ply PVC membrane that's part of when it was constructed in 1989. That PVC membrane is mechanically attached with battens. Then there's 2 inches of polyiso, a vapor barrier, and then there's the roof deck itself. Spaced across the roof are these sheet metal snow diverters that are anchored to hat channels and then attached to the deck. So one thing I can't emphasize enough is just how extreme Toronto's winters are, and the kind of conditions and burden that the original membrane and roof assembly withstood over the course of 30 or so years. But in addition to that, there's some really sort of unique conditions that are unique to the Rogers Center that put even a further burden on the roof assembly. One of them is the proximity to the CNN Tower, and that there's a really kind of a condition where ice builds up on the outside face of the tower, and it's just a certain right conditions that ice builds up, and then that ice falls down and plummets, and it's like a missile that strikes the roof from above. The other feature of it and is driven by that along the perimeter of all these different roof panels, there are these gutter systems. But I think gutter system is sort of a misnomer, because the size of these gutters is you could drive a truck through them. But that being said, what happens is a huge amount of snow gets piled up into these gutters along the eaves of the roof, specifically at panels 2 and panels 3. And it's something that at times it happens all at once, where the snow accumulates and builds up higher up on the roof. And maybe it's during a warmer day or what have you. Then all that snow rushes down the face of the roof and collects. And it really almost like an avalanche. And I think that's the best way to describe what happens when all that snow piles down, that dynamic force striking and certainly have an impact on the roof system. And here is just some photos of the kind of damage that the roof deck has experienced due to the falling ice and due to this sort of avalanche condition that occurs down at the eaves of the roof. And here, what we have is this is a section detail at the eaves. And this is just an image of a probe that we made of the existing roof system. And so in the photo on the left, what we're seeing happening is a combination of failures. And so partly we're seeing the sheet metal bent down, pop out the fasteners, and that's due to that buildup of snow. And so just that sheer weight of that is causing a failure, the buckling and the crushing of the overall roof assembly. But that's compounded by that you're having fastener pullouts, which is allowing water to breach the roof membrane and get into the assembly, soaking the rigid insulation, corroding the sheet metal and fasteners and the metal deck at these areas. But then on the right, we're seeing is a buildup of water. And this is water that's not just due to these failures in the membrane here along the edge of the roof, but failures that are occurring along the entire span of roof above this. And so what we discovered is that any failure, puncture in the roof, was allowing water to then travel down the top of the regulation and then collect down at the eave, the edge of the roof system. The other mechanism that water was getting in and coming down in this way was condensation. But we believe there was failure points in the vapor barrier where water was condensing up the underside of the roof and doing the same thing, and all collecting at this locations. At all the eaves, and some were worse than others, but it was something that this condition existed all around the perimeter and the different 4 panels of the Rogers Center roofs. And so that's a little bit of background of the kind of conditions that we found at the Rogers Center. And some of it is pretty extreme. Some of it's really unique kind of failures that it just a combination of extreme weather and then the construction, the geometry creates these really, really bad conditions, the adjacency of the Seaman Tower, that all coupled together created the kind of conditions we observed. And there was a long period of investigation that was part of this project where we did a full condition assessment. We walked, rappelled every inch of this roof from both the top and the bottom, many probes and investigative openings, infrared, 3D scans. It was really to get an understanding of what's going on and how this roof, this 30-year-old roof, has aged. And one of the things that we found was that it's aged really, really well. And although those images and what I spoke about before are pretty extreme, those extreme sort of extreme damage was isolated along the eaves of the roof. And so I think it might have been a jerk reaction to say, hey, all this roof assembly has to be replaced. But based off our investigation, based off the needs of Rogers and what they were looking for the service life of the replacement and the repairs, it made sense for a host of reasons that we're going to delve into, that were really the major repairs are going to be happening where the worst conditions occurred, and that's at that eaves. And so what we're calling an eave zone. And so it's the 8 feet sort of offset along the perimeter of these panels at the low point that a full replacement is going to happen. And then for the rest of the roof, it's keeping much of that assembly and just replacing the roofing membrane with a new membrane. And so that's the overall, that's sort of strategy that I think in certain respects is novel, that we took for this project. And so with these are 2 details of what was done at the eave. And so on the left is existing, the right is the new. And so starting off, it was all about strengthening to deal with that buildup of snow at these eave conditions. So that's that steel channel. That's adding additional sheet metal that runs along this edge on both within the rigid insulation and then above on the membrane, and then additional flashing over that. Like I said before, full replacement of all that assembly. So that's new vapor barrier, that's new rigid insulation, polyiso, that is new membrane. But then also, which I think is a really sort of unique feature of it, is that we allowed any water that does infiltrate this assembly, like what's happened before, if there are failures in the membrane, if there is condensation buildup that drains down, there's a mechanism of weeps installed at the base, and that this sheet metal is perforated to allow water to exit the assembly instead of allowing it to build up like what you saw in those previous photos. And so this is an image of what's going on with construction. And so it's, you look at swing staging for a roofing project, it's almost like facade work. And so they had custom scaffolding and swing staging to even get access to make some of these repairs. And here are further images of what's going on with construction. And what had to happen, where much of that roof assembly was going to stay in place, was that there had to be a level of control, quality control through the process of construction, where the assembly components that were going to stay, be that the rigid insulation, be that the vapor barrier, be that the existing roofing deck, it had to be confirmed that those were in good quality. Like those are absolutely essential components. Those are essential for holding down the whole assembly. And if they had deteriorated to a level where we didn't expect them, that had to be captured. And so a big part of this process and the success of the project was developing a really, really detailed work plan and coming up with a criteria where a crew that's on a swing staging knows the criteria, knows the steps of making that decision if something could remain or needed to be removed. And that all got first sort of in the beginning of the project, establishing that work plan. And then also through documentation, where each team had tablets where all the conditions were documented, and they had the information they needed to move forward and keep the project progressing. And so ultimately, there was two roofing contractors that worked on this project. They were able to complete construction in about 10 months, and that occurred through the summer during the baseball season, and also through Toronto's winter. And so it's all those sort of conditions that I spoke up in the beginning of the presentation, but they were doing construction where there's that risk of the build-up to snow and that avalanche effect, the falling ice from ceiling tower, closures because of high winds, you name it. And then the baseball season where Blue Jays are home, they took priority to our construction projects. And so working with all those sort of, I guess, those hurdles, the contractors, Flynn and Dean Chandler, did a great job in installing a high quality roof, as we've specified, in under 10 months. So yeah, like I think I can't emphasize enough the sort of challenges associated with this project. And so yeah, that is the end of my presentation. Does anyone have any questions?
Hey, Chris, this is Derek. Great presentation. Thanks for covering that. Mm-hmm. I wanted to ask you though, regarding just using the membrane, and excuse me if you touched on it, but just replacing the membrane versus replacing some of the existing vapor barriers or insulation areas. Can you talk about how were you able to determine, or how were you able to assess what you were going to be able to reuse? Did you make some assumptions there? And what kind of are some of the typical provisions or parameters or assumptions that you use going in on, all right, I know I'm going to have to replace the membrane, but how much of the existing vapor barrier and insulation can I reuse? Should I reuse it? And how did you assess that?
Sure. No, that's a good question. So certainly it started off with the initial assessment and us finding that in general, those components, those existing components, the rigid insulation, for example, was in good condition. And so that once that was established and was agreed upon, that's our approach, that could be reused. It was about how do we empower the contractor to make that determination where, yes, we were on site a good amount of time, but ultimately with the kind of geometry of this roof, we couldn't be with those crews in certain areas where they're on swing staging, where to keep things moving, they had to make their own decisions about if that component was good or bad. And so, for instance, for the rigid insulation, it was establishing a criteria of what's the allowable moisture content that can be in. They're going to have moisture meters on those rigs. What is an acceptable level? Is the facer ripped up? Are you seeing any physical damage? And it's these kind of checklists where each crew is provided those checklists where they have to go through it, and that gets documented on their tablets and through the construction progress software where they're photographing everything. There's that documentation, but also just kind of thinking through all the different scenarios, and those are captured in the work plan. So,
Hey, Chris, thanks for the great presentation. So I have a question, and what would you say was the most challenging aspect of doing construction in the winter and during baseball season? I know you touched on various challenges, but what was the most challenging and how did you overcome it?
Yeah, like I think the most challenging was in the winter, and we're certainly in the summertime. It was difficult, but it was more. We had the schedule. We sort of had control of when work had to stop and how to work around that schedule. But for in the winter, it was just these unknowns where it would change within a day that suddenly the wind would pick up, or there was the right conditions for icefall. And then it was the impact of the cold environment just on the material qualities of the new roof system. And so it was in terms of design, it was really limiting the use of adhesives. That primarily most of the assembly was all mechanically attached. It was also just understanding the limitations and that the roof membrane needed to be relaxed. It needed to be exposed for a certain amount of time to get that proper installation and get the sort of performance that's necessary.
If you could talk about the challenge of working with two contractors on the same project, and a little bit about why you what was behind the decision to use two contractors.
Yeah, no, it's a great question. I just sort of touched on it. But this project was unique in that it was required to have, it's really necessary to have two contractors, primarily because one of those contractors, Dean Chandler, had done the original construction of the roof. And it was actually, there was folks on their team that had done the original roof that were now involved in the roof replacement. And so that sort of ingrained knowledge, that skill set, an understanding of what's there and how it performed so well over 30 years was absolutely crucial. And so we were thrilled to have them part of the team. But on the flip side, it was the intent of the client, Rogers, was to finish the project as quickly as possible. And through the winter, through the baseball season, and was all successful in getting it done in 10 months. But to do that, we needed to have two different roofing contractors. And that's at least my understanding, how Flynn got involved. And it was great. What we were doing was, in certain respects, we were getting double submittals. We were getting double shop drawings. We were doing two different mock-ups. But what I found really, really interesting is they sort of gained the knowledge through each other, where they're working on the same roof. There was a lot of collaboration, certainly not competing against each other. But in doing the mock-ups, one of the teams would learn something and say, hey, like this approach really, really worked. You have a similar condition on the other panel. Can we implement that? And the same thing for the shop drawings and the submittals. So I think it worked out really, really well because it was a community or a culture of collaboration. So.
Hey, Chris, I also had a question in the chat. I was wondering what were the quality control measures for the new roofing components that were installed?
Just going to that detail at the eave, there's quite a lot of complexities to it, and it's sort of unique use of the sheet metals with the weeps, and so I think we had 2 or 3 different mock-ups of this really similar condition and sort of working through exactly how that happened, how that was constructed, what's the sequence, what's the best approach on how to do that. And so I think that was one of the big drivers in terms of quality control. These eaves areas were a little bit easier than the rest of the roof where the existing components were staying in place because it was accessible. So it was at the low point of these roofs. Many of them, you didn't have to go in swing staging. You didn't have to get up in the air to see. So I think the combination of that made a real difference. So.
Hey, Chris. And can you kind of expand on that process of removing the old material and installing the new roofing materials?
Yeah, absolutely. And for at the eave zone, it's typical to what you would see in a typical roof replacement, where there would be a complete tear off all the way down to the roof deck. And then similar to what I talked about the work plan to assess the rigid insulation, we had a similar work plan that focused on the metal deck. And so a sort of checklist about how it got evaluated, what's the level of corrosion. And that was a little bit more hands-on because it's a structural component of the roofing assembly. So we were more involved in that, where any defect became a bigger deal, but it was still a very, very detailed work plan about what's the level of deterioration and what are the different approaches to the repairs, and that gets all captured in the software, the construction scheduling software that we utilized for the project. So yeah, like and then at least at these eave zones where we're putting the new assembly, then it's getting that vapor barrier down. It is fastening down the rigid insulation, and one of the unique features was just the sort of different wind forces, the design uplift requirements for all the different components of this roof, and depending on what area you are, what elevation, it all dictated the amount of fasteners that were going to be required for the original insulation. And then the roof membrane was attached mechanically with a batten and then flashed over. So in general, that's the approach for the new assembly.
Chris, I think there was one more here. I don't know that this one came through or not. This question was just posted, I believe. Were there, and I'll read it, was there any varying conditions, or were there any varying conditions on regions of the roof facing south or north, which over time may have affected the general performance of the existing roof system? I believe that maybe kind of specific to, did you see anything localized in particular areas? In this case, he's asking north or south. Maybe you can expound on that.
Yeah, I'm trying to think if there was anything that really jumped out that came about during construction or even during the investigation.
I don't know if you noticed worse oxidation perhaps on the membrane on the south face, or maybe more microbial growth or biological growth on the north facing side. You hit on it. Some of the damage to the roof was due to adjacent structures and falling ice and things like that. But don't know if you saw any advanced oxidation or perhaps any microbial growth on the south or north sides, respectively.
Like one of the things that does come to mind, which I don't think I've seen in other thermoplastic roofs, and I believe it was because of the sliding ice and snow, where it appeared to be the loss of plasticizer just caused by that friction, where you'd see that due to that force of that ice coming, and that would expose the reinforcing within the roofing membrane. That was definitely something that I can't recall exactly where that was worse, but that was one feature that we saw that is sort of unique to this roof.
Well, Chris, I certainly appreciate you giving us all that presentation. Fantastic information, fascinating story, and an amazing project. I think that's all the questions we had, and I think with that we can conclude. But again, thanks for your time today. Thanks for all that attended, and we hope you'll tune in again for our next MooreChat coming up soon.